Thank you, Holger. So, let's get this. There we go. Good evening. So, Scala, Akka, and Docker. First of all, well, who am I? What am I doing here? Don't we all ask that question at some point in our lives? Well, in this particular moment, I have been working with Scala for quite a few years, since 2009, something like that. Having been working with Docker quite a bit less, and I recently moved one of my personal projects to Docker, and I'm also looking at how we can leverage Docker within eBay. We are actually using it quite a bit, but we are thinking of moving some of the applications that we are currently working on over to Docker. Okay, and I'm working, well, as Holger said, at EPD, the European Product Development Organization within eBay. So first of all, let's talk a little bit about what Docker is. Then we will talk about what Docker brings to Scala, what Scala brings to Docker, and finally a little bit about Akka specifically in the Docker ecosystem. So, how many of you have heard of Docker? Everyone. How many of you are actually working with Docker? Okay. So let's start with, for those of you that have not been working with Docker, let's start with a little bit talking about what Docker is. So first of all, according to the Docker website, it's a way to package, ship, and run any application as a lightweight container. That's quite elucidating, right? We can basically end the presentation here just with this phrase. But what Docker is basically a way that you can take your application and you can package it in such a way that it can directly run on almost any infrastructure. Well, almost, there should be an asterisk over there because it's basically Unix-based, and not all Unixes work underneath Docker, but the idea that you can more easily package and distribute your applications. Okay? So normally, we've all been there, right? You take your source files in a normal, with non-Dockerized way of building, or non-Dockerized build pipeline. So you take your source files, you pass it through build system, through Jenkins, through Travis, through whatever, it uses SBT or uses Maven or uses Gradle or uses whatever. And you eventually get out some artifacts, usually jar files, some configuration files, scripts, etc. Right? The problem usually comes after that because you have your artifacts. You're very nice. It's Java, it runs on the JVM. But then you have to deploy those artifacts to whatever platform you're running on, whether it's AWS or an in-house cloud or a server in your garage or in the back room of your house. And of course, there are probably as many different ways to deploy as there are projects out there. And there are a bunch of other problems because aside from deploying, there's a bunch of stuff in here that you have to worry about. Things like, is Java actually installed on this machine? Is the correct version of Java installed on that machine? And it turns out that the sysadmin thought it would be a good idea to move from Java 7 to Java 8. And yes, there are a few incompatibilities. And suddenly your application grinds to a halt because somebody did something to this machine that you have no control about, that you have no control of. Or perhaps your test environment is running on, say, on Linux. Your production environment might be running on something else, or perhaps another Linux distribution. You might have different versions of the JVM. You might have different configurations in the machines. And this turns into a complete mess. So what does Docker bring to the table? Well, you still grab your artifacts, but instead of deploying them directly in the machine, you assemble something that's called the Docker image. And we'll talk about images in a moment. But it's basically a self-contained file that contains your application code with all of the dependencies that it needs. Okay? Next thing you do usually is you publish that image into something called a registry. So it's kind of like GitHub. You publish the image, you upload it to some server, and then all of the platforms that you're running on, whether it's your CI server, your test environment, your QA environment, your production environment, get the exact same image, the exact same bits from that registry. And actually Docker, here are some examples where it can run. It can run directly on Linux, and there are two different ways of running Docker on Linux. It can also run on Solaris. It can also run on, there's something called CoreOS, which is kind of a very, very minimal, bare bones operating system designed to run images on top of it. BSD also works. So again, some Unix environments, but the idea again is that you have you have a minimal operating system and minimal dependencies on the operating system. So we talked about Docker images. So the idea here is that a Docker image is a way to package your application together with all its dependencies. What do I mean with all its dependencies? Again, the JVM. If you need any shared libraries because you're calling into native code, any shared libraries you might need. Any configuration files, everything, that is contained inside of the image. So the idea is that the image is completely self-contained. It's kind of like a mini Unix system isolated from the rest of the machine. They're, again, stored centrally. They're stored in a single place where everybody gets the images from. Again, the registry will also version the images, so you can actually very easily roll back to a previous image if you find something is wrong with the latest one. Okay? And it's basically, well, a snapshot of a container. So what is a container? Turns out that when you start an image, that image gets started in what we call a container. The container is actually the runtime representation of the image. Okay? And the container is completely isolated from other containers in the machine. So it has it's actually using Linux namespaces, for example, when running on Linux, so that the processes that you're running on a container are completely separate from the processes that are running on a different container. So say a hacker hacks into your web service. He can only get access to the Linux system that's inside of the image. He cannot get access to the whole server or the VM that it's running in. It also has its own file system. It has its own networking. It's completely isolated from the rest of the system. Like we said, it's OS agnostic with a start in it. I mean, in the sense that the image can be deployed onto any operating system that supports Docker. So you cannot deploy it directly on Linux, directly on a Mac. If you want to deploy Linux on a Mac, you usually use VirtualBox, and you deploy to a Linux VirtualBox instance that's running on a VM. It is also very much lighter than VM. So far, it sounds a lot like a VM, but this is very much lighter than a VM. So normally, when you're running virtualized environments, you're running KVM, VirtualBox, whatever. Basically, you've got your host. Then on the host, you have the kernel and a bunch of daemons that are running there. And then each virtual machine is running a full kernel image and a full operating system and a full set of services. And that, of course, takes a long time to start, sometimes a long time to stop, and it also puts load on the machine. If we go back, another thing is that that's better here. Another thing that you'll find is that inside of a container, you will usually run a single process. You will run just your specific web service. You will run only your database inside the container. You don't usually run multiple processes inside of the container, and that helps you to isolate one process from another one. So the way this usually works is you have your host or virtual machine, you have your kernel, you have your host file system, you have your host with all its daemons and whatever, and then you have different containers running each of your services. Okay? And each of those containers, again, will usually run a single process. Now, what you then have is you can, of course, connect ports from the containers to the external world, or actually connect them between the different containers in a single machine without having to expose them to the rest of the world. And then you've got the Docker registry. You've got a local index. Basically, when you want to run a container, you want to run an image, you talk to the Docker daemon that's running on the machine. You tell it to download an image from a specific image from the Docker registry. It gets pulled in here, and then when you start up, you create a container from that image. Okay. Now, why do we want this? So far, this is a little 10,000 foot view or 10,000 meter view of what Docker is. So why do we want this? Well, first thing that Docker gives us is it helps us with dependency management and with environment management. So, for example, the example that I just mentioned, the JVM. The Docker image contains the JVM, whatever version of the JVM you have tested your application running. So you don't have any problems with the production server running a different patch level of the JVM or different version altogether, or your application runs in Java 8, but the sysadmin won't install Java 8 on the machine because it's outside of whatever policy they have, so they can only install Java 6, which has happened to me. Has that ever happened to you? You have to run Java 6 because the sysadmin says that we can only run Java 6? No. It's not nice. Okay? It also includes all the libraries, so aside from the jars, it will also contain any native libraries that you need, any additional processes or any additional programs that your application needs to run, any startup scripts, stop scripts, whatever, and all of your configuration files. And again, all of that is in a single file that gets deployed, the same file that gets deployed everywhere, okay? However, you have all of this, but the image is also created from a text description. So many of you have probably worked with Puppet, with Chef, with those kinds of things where you basically have a configuration file and you have infrastructure as code. You have a text file that defines your infrastructure. So this is kind of also one of the advantages of Docker. Every single change you made is actually it's actually reflected in the Docker file, and it's also, of course, controlled in version control. Okay, so it also gives us a lot of what we have already learned with Puppet, Chef, Ansible, or whatever infrastructure as a service. Infrastructure as code platform you are currently using. Okay, now. Aside from that, we have a standardized infrastructure in the sense that your application is independent of the underlying OS. It's independent of the Linux distribution. So you might be running, again, Debian on your machine or Ubuntu on your local machine, but the company has a license from Red Hat and they are running Red Hat Enterprise or whatever it's called lately on their production servers, but they don't want to spring to have Red Hat Enterprise for all the developers. So in this case, you wouldn't have a problem with that because again, the whole environment that the application is running in and the whole environment that the application sees is contained within the image. It doesn't really interact with the base operating system that it's running. Okay, so it gets rid of a lot of things like, well, this works on my machine. Turns out it doesn't work on the production. It doesn't work on my colleague's machine or on the on the QA server because somebody touched the host file or modified the DNS configuration or whatever. It's the same configuration everywhere. Works on QA, doesn't work in production, or vice versa. I think several of us have probably been there. Okay. Another thing about Docker, and that is, I mean, so far, most of what we have seen here we can probably get with Chef, with Ansible, with Puppet, in different ways. Some of the stuff, especially the process isolation, we can't, but all of the configuration, infrastructure as code, standardized infrastructure and so on, we can get there, right? However, another thing that Docker gives us is that it promotes the use of what we call ephemeral and immutable infrastructure. What does that mean? Well, first of all, when you update your machine, you really do not update the machine. You basically destroy the container and recreate it from the image. The advantage of that, it actually promotes that any configuration changes are actually reflected in code and reflected in version control. So no more, well, let me just log into the machine and make a hotfix just because it's the fastest way of doing it, and then somebody forgets to update the Chef script to actually make that change permanent. Well, in Docker, let's say you could do that, but it's harder. It makes it more difficult to do that kind of thing. Another thing is that, especially in the cloud, especially when you're talking about scaling up, scaling down, one thing you really want is to make sure that your machines can come and go, that you don't really keep any permanent information or any information that you really care about inside of your machine, because the machine, again, it's a virtual machine that can run that can die at any time. So, since the image is immutable in the sense that you will not modify the image in runtime, then, I mean, you can modify, you can edit files there, but you are very aware that that is a very, very temporary state of affairs, and that you will be, that image can go at any time. So it encourages you to think about these kinds of things. So that also means, like we mentioned, every changes in VCS, we do not have another thing, for example, logging into the server and running apt-get update, and suddenly something stops working because one of your dependent packages, somebody updated to an incompatible version of libc that has a bug, or something like that. Well, the packages that you are running are actually burned into the image, so you will not update the image. You will not go into the image, and you will not update the running container. You will actually update the image, upload the image, and then recreate your machines with the new image. And that means that all the machines are running the same software, are running the same versions, are running the same everything. Okay? So that's, again, there's a lot more. I'm just giving a 10,000 meter overview. Okay? So how do we usually work with Docker? Well, first of all, we need to install Docker. We need to install the Docker daemon and the tools to build Docker images. We really need to install those on every single machine. Basically, all the developers' machine, the CI server, because usually you have your CI actually generating and pushing your Docker images to the production, or getting, to the registry, or getting the image from the registry and running your tests. Of course, all of the production hosts and so on. Now, if you're lucky enough to be in Linux, all Linux distributions have some sort of Docker package. So just apt-get install or whatever your package manager of choice is. If you're running on OS X or Windows, it's a little bit more complicated. However, the people have actually created something called Docker Toolbox. By the way, the presentation is live on the web, so with, of course, all clickable links and everything. And at the end, I'll post the URL. So if you want, you don't have to actually, write down any URLs or ask me what the link to Docker Toolbox is. Okay, so you can you can later peruse it at your leisure. And what that will do is it will install VirtualBox on the machine, and it will run Docker inside of VirtualBox. So once you have installed Docker, then you want to start creating images, right? So a little bit of Docker concepts. So Docker image is built in what we call layers. So basically, you have your Docker file. We'll see an example in a moment. And the Docker file has a series of directives. Each of those directives is actually actually gets built into what we call a layer. It's a copy and write file system. So you basically it creates you get an initial image. On top of that image, you run a particular command, and it creates another layer. So it kind of creates another image on top of the other one, another image on top of the other one, another image on top of the other one. So you could say that a Docker image is not just actually a self-contained file. It's actually a series of layers, each one of which is actually a Docker image. And that's important when you're actually creating your Docker file. You want to think about what layers you actually want there and in what order you want to do things, because of things like caching. So again, you start with a base image. You get a base image from a registry. So you might get an Ubuntu image, or you might get an Ubuntu that already has Java installed, or Alpine OS, or Core OS, or whatever image you want. And then you start adding layers, things like, well, I need this additional tool. I need the JVM. I want a bash shell so that I can log into the image, whatever. And then at the end, you add your application binaries on all of your configuration files. So this is an example of a Docker file. We start from a specific base image. By default, there's a registry called Docker Hub, which is the default registry, but you can also have private registries, and there are also some other public registries on the internet. Then I'm running some commands. And you see here, I'm running them as a single layer because it's a single run command. If I did run, then it would create a layer for each one of these commands. I'm installing some additional packages I want to have on that image. Then copying some files from the source file system, from my computer's file system to inside the Docker image. Then I tell the image, when you start the image, what command will you be running? Sorry, that's the entry point, sorry. Then I run another command, just change some permissions. I create a user, and then I tell it, okay, when you start up, you will run this script. And you see here this /srv, that's the name inside, of course, of the image, which is where I copied this script here. Okay, so that's an example of a Docker file. And then when you want to build an image, you just do docker build to tell it the directory where the Docker file is. Okay? And then you can actually see how each of the intermediate images is built. Okay? Now, once you have created the image, how do you run it? Well, first of all, you can actually do docker run and give it the hexadecimal hash of the image. But what you will usually do is push that image to a repository, to a registry, sorry, and then when you want to run it from another machine, you do docker pull, and then you do docker run. And this is a tag. You usually have a tag called latest, which is the latest version, but then you have tags for each of the versions of your image that you have uploaded. But you will usually use, the most common usage pattern is to use the latest tag. Now, some things you have to consider when using Docker. First of all, well, again, ephemeral, immutable images. Anything you care about should not be inside of the images. So if you write to a log file, that log file will get deleted the next time you recreate the container. So you want to have centralized logging. You want to push those log messages to a database, to some service, Logstash or whatever, that actually stores your log records for you somewhere else. Same thing, all your data sources. Data sources, you should be getting your data from somewhere outside of the image. If it's files, you can actually mount, it's discouraged, but you can mount from the source file system, from the host file system, you can actually mount things inside a Docker container. But usually you want to use things like remote database, NFS, something like that, just again, so that you are not holding important data inside of the container. You will usually have all of your configuration files inside of the build. So you have multiple configurations. You have a QA configuration, you have a development configuration, you have a production configuration. You need to include all of them in the build, and then at runtime, select which one of them. When you actually start the container, when you're running the container, select which one of them to run. We'll talk about config files in a moment. And for things like dynamic configuration or selecting which config file to run, you can actually pass in environment variables to the Docker command. Okay? Networking. Networking, Docker uses a virtual network interface. What that means is that by default, the machine does not have access to the outside world. It cannot listen to the outside world. It can talk to the outside world, but it cannot listen. So you basically need to do port mapping. The problem with that, of course, is the Docker itself adds some network overhead. That's gotten a lot better in Docker 1.9. In Docker 1.8, there were some benchmarks that actually saw reductions of 70% less network bandwidth. It's gotten a lot better in 1.9. And of course, for extreme cases, you have this little flag called net equal host, which basically says expose the virtual network interface. Just don't do any mapping, just expose everything to the outside interface. That can be a security problem. That can also limit the number of containers that you run, because if you have several containers that are listening on the same port, well, you're in a problem if you're using net equals host, but there's another solution, okay? Now, that's Docker. Again, very quick introduction. There's a lot more information in the web, but of course we have a limited amount of time during this talk. So let's start now to see how to integrate Docker with Scala. So first of all, we'll start just by Dockerizing a Scala application. You have your normal Scala application, and you want to run it inside of a Docker image. So the first thing you need to do is create a Docker file. So you want to select a base image, and inside Docker Hub, there's the Java OpenJDK 8 image. That was a good starting point. It's based on Ubuntu and OpenJDK, and they actually have even up to Java 9. So you can actually create images using Java 9 if you want to start testing. And here's, of course, the link to the Docker Hub repository. However, there are some issues with that base image. First of all, it's running OpenJDK, and your application might need the Oracle JDK, for example. That happens. Or Actually, the other problem that it has is that it's quite big. It's actually including a minimal Ubuntu distribution. It's minimal, but still Ubuntu. That basically means that the Docker image, the official OpenJDK image, is about, if I remember correctly, it's about 200 megabytes, just the base image, which is a little bit large. Okay, so there are other images that are not the official image in Docker Hub that use other Linux distribution. Alpine Linux is quite popular because it's basically a very, very minimal Linux distribution, very minimalistic for running inside of a container. Okay, and you can actually roll your own. There are some articles on the web as to how to roll your own image. So you basically take a base image that has just the bare Alpine Linux. You install whatever you need to run the JDK, and that you can probably get images that are half as large probably as the official Ubuntu image, or even less. And of course, making the image smaller means that it takes up less bandwidth and less time to upload to Docker Hub. And it also means that it takes up less disk space in your servers. Of course, disk space right now is free, but bandwidth is not necessarily. So, again, we start with a from line. We can actually say from Java 8, Java 9, Java 7, and that will just grab the latest Java 8 image out there. Or, for example, in this case, an image that's already out there using Alpine Linux. Okay? You have your image. Next thing, some things you usually want to do, things like, for example, update any packages. Some people actually are saying that inside a Docker you should never run apt-get update because your image should be stable, and the next time you recreate the image, you don't want to have unexpected package updates. And that there are differing opinions on whether you should be running apt-get update inside your Docker file. Okay? Things like, for example, generating locales, for example, adding a user if you don't want to run your application as root. Your application will always run as process ID 1, and by default it will run as root inside of the container, which doesn't mean it doesn't run as root in the host operating system. So again, some commands to run. Now you add your code. What I have found easiest is to just generate a fat jar. So use, like it says there, SBT assembly, SBT native packager, or whatever tool you want to use to just generate a single jar. You can actually just copy all of your class files, but it's just a lot simpler just to have a single jar that has the whole application. You use the copy command. So you see here you copy from target Scala 211 myapp.jar to this directory inside of the image. And then configuration files. So a couple of notes about configuration files. There are three options. First thing you can do, suppose that you have your development, your QA, and your production configuration, and they have different values for some configuration variables. The first thing you can do is you can actually have separate Docker files and separate images. You have a QA image, you have a production image, and you have a development image. Nice thing about that, you don't have to worry about picking the correct configuration file when the container starts up. Bad thing about this is that now you don't have the same infrastructure in development, in QA, and in production. And it also doesn't play nicely with some of the stuff that we'll see later about integrating Docker with SBT. The other option is you could have one image and have separate config files. So you can have a directory per environment and then have copies of the config files in every single, for each of the environment. Problem with that might be that you're actually duplicating a bunch of stuff between the different environments that should be the same, or you have code to actually do a merge. You can use type safe config for that for those kinds of things, but it can get sometimes a little bit hairy. But what I'm currently using, having one image, different config files, and different directories for each one of them, and then we pass in through an environment or variable which directory do I want to get the config files from. You can always use a single config file and then just use environment variables inside of the config file, and then just pass in all of the configuration changes from the command line to the Docker run. The problem with that is that it can, if you have a lot of environment-dependent configuration, then that file can get a little bit hairy, and the command line can get quite long just because of all the environment variables you need to pass. So my preferred option is just using using different config files in different directories. One per environment. Okay, so in this case, for example, copy the shell script that actually starts the application. I have an etc. directory inside of my source, inside of my my project directory, where I have all the config files that need to be copied to the server, and they live in SRV, etc. Chain owner, change mod, user, and start run.sh. And that would be basically the Docker file. I don't have room to put the whole Docker file here, but that would be those are the different pieces of the Docker file. Once you have created your Docker file, then you just compile your application, assembly, you run SBT assembly or whatever you want, and then run Docker build, and then you can actually push the image to the repository, to the registry. I keep getting that name wrong for some reason. So that's easy. You can do that with any application, not just the Scala application, but of course, this is Scala. We can do better. So why not try to integrate Docker inside of SBT? Well, why do we want to do that? Well, because we can. Why not? Right? We should integrate all the things. But actually, there are some advantages here. First of all, you can actually integrate this into your build pipeline. So you run everything from inside of SBT. You don't have to remember to compile and package your application before creating the image, which is nice. You can also use it for running integration tests, and we'll be getting into the use of Docker for integration tests later. Okay, so there are two different plugins, SBT plugins, that can generate Docker images. We have SBT Docker and we have SBT Native Packager. SBT Native Packager recently added the possibility of creating Docker images, but the one that I'll be talking about right now and that I've used is SBT Docker. And SBT Native Packager can do most of the same things, only of course the syntax will be different. But if you are using Native Packager for something, you might prefer to use it. Okay? So the thing about SBT Docker is that first of all, you define your Docker file inside of your build file, inside of your build.sbt or build.scala. So you don't have this separate configuration file out there. And you can also then create the image and push the image straight from SBT. Okay, so how do you do that? Well, first of all, of course, you add the plugin in the plugins.sbt in the plugins.sbt file. Once you have that, first thing you need to do is set up what images are you going to be creating, right? You need to tell it. It's called a namespace. It's actually, for example, in Docker Hub, it would be the account name. Okay, they call it a namespace inside SBT Docker, but it's actually the name of the user under which that repository lives. Then repository is actually the repository within the registry, and that will usually be your application name. So in this case, if the application were called foo, then this would create an image called mcamu/foo. Okay? And then you need to give it a tag, and you usually want to publish two different tags. You want to publish one with the actual version name and one with the latest tag. Now, this will not actually push the code twice. It will just basically create a symlink inside of the registry saying that the tag latest actually corresponds to this other version. That way, you always have your version history updated in the registry, and you always have latest pointing to whatever the latest image is, so which makes deployment a lot easier. So if you got your image names, okay, if you see it's a sequence, so you can actually make more of them, but you usually want to have at least these two. Then once you do that, well, these are some vals I will usually use. First of all, the artifacts. So again, a fat jar. We need to get the name of the fat jar, so that's some SBT magic to get at the actual fat jar that SBT assembly produces. Then what directory inside of the image will I be storing files on? And if you see here, these are the same commands that I was running in the run command in the Docker file. Okay, so it's just a series of commands joined with ampersands. Okay, so again, this is just, I mean, you can do it inside the command, but of course it's nicer to just set it up in to just set it up first. Now, once you have that, then you configure your image, and for that you use the Docker file in Docker task. Okay, so you do create a Docker file, then you have run raw. You have run raw basically receives a string. You also can have run when you will actually pass an array of each of the command line arguments that you want to use, but usually run raw is a lot simpler. Then we have the copies that we have. Copy the artifact which is the file that we set up here. Copy your artifact to wherever you want it. Copy your etc. directory. Copy, and the names are a little bit different from the previous just because I refactored some part of the presentation. I didn't refactor the other part of the presentation, but it's basically the same thing. Okay, what user, entry point instead of entry point. Again, you see that these commands are the same thing that we put in the Docker file, and actually SBT Docker will use this to generate a Docker file for you. Okay. If you're running SBT assembly, you really want to always run the assembly task before running the Docker push or the Docker build. So we can actually add to the Docker task, we want to make it depend on assembly. So that means that you then only need to do Docker to create your image, and that will run your assembly. You can also, for example, run all of your unit tests. You can add a dependency to run all of your unit tests before building the Docker image, and so on and so forth. And again, that depends on how you want to go about it. Once you're done that, then you actually have two commands. One called Docker that creates the image, and one called Docker push that will actually push the image to the server, to the registry. Again, a lot simpler from the build pipeline perspective. Okay, so some recommendations when using SBT Docker or SBT native packager. Well, again, it's a lot simpler if you create a fat jar. It's a lot simpler to use that than to just copy over all of your class array, all of your dependencies. Sorry. Now, this is one I put it here because it always bites me. I always forget to do it. So I'm running on a Mac, and if you remember, Docker runs on a VirtualBox VM. And I always forget to start up the VirtualBox VM before starting SBT. So you need to start up, use Docker machine, which is part of Docker Toolbox, to start that actually starts the VM, starts the Docker virtual machine. And then you need to give this incantation to set up your environment variables so that your Docker command line will actually talk to the Docker daemon that's running inside of the VirtualBox machine. If you do not do this, the Docker command will actually try to talk to localhost. And of course, Docker is not running a localhost, so things will fail, and you have to exit SBT, start everything, and start up again. Okay, so again, I just put it here because it's something that always bites me, and still, up to this moment, I forget to do it. So that's the first step, right? You can actually use Docker to deploy your Scala applications. What else can Docker bring to the Scala ecosystem? Well, next up, let's talk a little bit about integration testing, right? So what do you do if you want to set up and run your integration tests in some machine, say on your local machine? Well, integration testing will actually test interactions with some sort of database, some sort of message queue, some sort of a web service, some sort of MongoDB, some sort of something. So a bunch of external services, right? And setting all of that up can be a little bit complicated. Either you have a dedicated QA environment that all developers work against, which then comes to the problem of, oh, somebody changed the permissions on the test user that we are using because in some other test they changed the permissions and suddenly the rest of the integration tests stop working. For some reason you don't have a connection to AWS, so work stops because nobody can run the integration tests. So ideally you would like to be able to run your integration tests on your machine with the whole integration environment running on your machine. So one first solution is, well, why not create Docker images with all of your dependencies? So if you depend against MongoDB, well, create a Docker image with a MongoDB, with a database in known good condition, And then every time you want to run the integration tests, you start up the container from that image. Your database is in a known condition. It's running on your machine, so there's no connectivity problems, and you can actually run the integration tests, okay? And same thing for every single other dependency you have, right? So for each of the containers, you have to manually start them up, then wait for all the containers to start. Once you're sure that all the containers have started, then you run all of your integration tests, and then you have to remember to stop the containers, otherwise they'll just wasting memory and CPU. There's got to be some simpler way of doing this, or at least to automating this, right? Well, turns out there is. And there's another, there's a library called Docker IT Scala. So what that does is it basically allows you to define Docker containers inside of your integration test code. So take this example, okay? We have an application that depends on MongoDB, okay? So we create this trait and it extends something called Docker Kit. That's part of Docker IT test. And we're basically saying, well, I want to create a container based on this particular version of Mongo. Or it could be based on an image that you already have in your registry that has Mongo with all of the basic data that you need, okay? And I want to map these ports. And this is the way I'm going to be checking that the container has actually started up, okay? And this is the command I want to run inside of that container, okay? And then you have this Docker containers, that's part of what you extend in Docker Kit, and you need to override it and just add basically your container to that list. So what this gives us is now that the tests know that there are these containers that you are using, okay? Now, here's where the magic starts, because what you then do is you mix in that trait into any of your integration tests that need that service. So here we have we have a test that actually depends on Mongo. Okay? So all you do is add this, and when SBT runs, it will actually know that before running this test, it needs to start up the Mongo container. It needs to wait until the test started, and then it can actually run this. And it will shut down the container once the tests are finished. And it will actually not start the Mongo container every time for every single test. It will start the containers, so it will be smart about it and just start just those containers that are needed for those tests that you are running at a particular time, but it will start them all at the beginning and stop them all at the end. Okay? First time I saw this, I said, this is sweet. This is really nice. Because it really makes things, you do have to have all of this set up, and you do have to set up your images. Once you have set that up, then writing the integration tests and making them work is a lot simpler. It's very, very much simpler. Okay? So that's it about integration testing. So let's talk a little bit about Akka. Yeah. I was thinking, I had two sections that I thought were the other way around, but yeah. So, Docker and Akka. So first of all, Docker is really nice for elasticity in the sense of starting up and shutting down machines. If you're running on Google Cloud, you have Kubernetes that will actually do all of the Docker startup and shut down of machines for you. If you're running on AWS, you have the Elastic Container Service, ECS, that will also do that for you. It's basically not starting up machines, it's just starting up containers, and you tell it what containers to start when, and so on and so forth. All of them have actually, like we said, orchestration. Since your images are immutable, you don't really have to care whether, you don't have to care whether especially when you scale down, that some vital data will be lost because some machine got destroyed. And when you're scaling up, the containers start up really fast because the virtual machines are already running. Akka, as we know, is also very nice for elasticity, right? I mean, we have Akka cluster. Okay, we have Akka that actually enables us to transparently join new Akka nodes and have all the rest of the Akka nodes transparently talking to them. You have the location transparency thing, cluster-aware routers, so that you basically send a message to an actor, and that actor can be in a machine that's already there, or it can be in a machine that suddenly came up. Okay, so this is kind of like chocolate and peanut butter, right? Well, so there are some caveats with Akka. First of all, if you're running on Akka 2.3 or less, you have to use net equals host, because Akka gets awfully confused by port mapping. So you have to do a one-to-one mapping between your host network interface, your host network ports, and your container network ports. If you're running on Akka 2.4, there are actually configuration options to set up the internal port and the external port separately. Okay? And this is, of course, an FAQ inside of the Akka. This comes directly from an FAQ in the Akka site. Another problem is clustering, because, and I mean, we pop up, not even with Docker, you also pop up, this also pops up whenever you're running in any sort of virtualized infrastructure, right? I mean, Akka clustering says that you need to have at least one seed host that has a well-known IP address. It turns out that if you're in Amazon, you can actually, or in one of the big cloud providers, you can actually have public IP addresses and have them linked to your virtual machines, but that's a bother. And now if you're running containers inside of those virtual machines and you don't know when they're coming up and coming down, well, it's kind of hard to actually get the seed hosts. So first thing you can do, there's a couple of commands. That's Docker 1.7, that's Docker 1.8, that can actually help you link virtual interfaces within your Docker containers, even across, in Docker 1.9 you can even do it across the network, so that you can have virtual known IP addresses that don't map to any real IP addresses. You can do that. There's also, the Docker guys have this Docker Compose tool that will actually help you also set up the network that way. You can always roll your own. So instead of using the standard Akka way of finding your seed nodes, you can actually use, for example, Amazon's SDK and use, for example, a tag in one of your servers and know that that is your seed node. And you can use the SDK to query that, to query Amazon's deployment database and find the seed nodes instead of just using it, setting it up in application.conf. There is also a project that uses Zookeeper for seeding Akka clusters. So if you already have Zookeeper somewhere running somewhere, that might be another option. And TypeSafe, well, sorry, what was the new name? Lightbend? So Lightbend, I need to update that slide. Lightbend also has a product called TypeSafe Conductor or Lightbend Conductor. Of course, that's part of a Lightbend subscription. But that can also help you with this kind of thing. So there are solutions around there, nothing that works straight out of the box, except perhaps for using Docker Network. But there are some solutions around there. Okay, so finding the seed nodes. Here are some references of the stuff that I just talked about. So aside from just being able to, yes?
What's Akka?
We'll talk about that later. Akka is actually, it's a mountain somewhere in, was it Finland or Sweden? Okay, so aside from just auto-scaling, what else can Docker bring us bring to the table as far as Akka is concerned? Well, you can also use Docker to make some testing of Akka. So for example, suppose you have an application that depends on Akka cluster and is using Akka persistence. Have you set up your persistence correctly? What happens to that application when a node suddenly goes away? And how do you test that? How do you make an automated test that can start up a node, blah, 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 then kill that node? I mean, you can, but it's not necessarily easy, right? What happens when a server is down, so on and so forth? Well, there's another library called Reactor Docker. And what that will do, there's actually a Java SDK for Docker. Well, this is nicer. It's actually built in Scala and built on top of Akka. And it will allow you to do things like, well, start this container with a certain timeout, okay? Create the container, start it, stop the container, and so on and so forth. It actually gives you it gives you control over your Docker containers at a very much lower level than Docker IT Scala gives you. Okay, so that, for example, you can also use to start up some containers that you need for some testing, for example, or to orchestrate all of your stuff. And that again, that's reactive Docker. Okay, so there's a very good presentation by Andreas Gies that where I actually got some of a lot of the information that I'm putting in here, and he actually goes a lot deeper into using reactive Docker. Oh, by the way, back here, this presentation by Heiko Seeberger from last December's Scala Days is really good. Akka cluster on Core OS. Okay. So, to summarize, and I think I'm just in time. That's weird. That feels weird. So, what does Docker bring to the table here? First of all, it's a technology to ease application deployment. Okay, it can be very nicely integrated with SBT so that you can easily integrate it with your build pipeline. Okay, you can increase elasticity and ease of testing and so on and so forth. And of course, for integration testing, it's really useful. Here's where you can find the presentation. Okay, actually, this is my personal blog. I should probably put it in the eBay blog somewhere. But this is my personal domain, and this is the presentation is there. And it's hosted on GitHub pages, so you can actually go to my GitHub and have a look at it and pull request or submit it to you.